Okay, we're about to do the mean and variance of a random variable, and this brings us right up against something that is potentially confusing, but you're going to get used to, you're going to need to. Okay, we now have two symbols for the mean. X bar, which we used when we did data, is a sample mean. In other words, we've gone out and we've got 50 or whatever items of data, and we've worked out the mean of those 50 values. Okay. We now are thinking about the mean of a distribution. Okay, so if we look at one of the probability tables that we've been working with here, okay, we know absolutely everything there is to know about this distribution. So if we did this experiment 100 times, then on average in the long run, okay, 10 times out of 100 I'd get 0, 15 times I'd get 1, 25 I'd get 2, and so on. Okay, now if I actually only do it 100 times, I won't get exactly those. So my mean of those 100 trials would be an X bar. If I can imagine myself doing it an endless number of times, so that all the random effects fluctuate out, on average, overall, I should get exactly 10% noughts, 15% ones, 25% twos, and so on. So we've ignored all the effects of getting one particular sample rather than another, and we've gone with the underlying probabilities. Now when I do that, I get an underlying feature of the distribution, which is called the distribution mean. Okay, and that never changes, so for different samples I'll get different sample means, but the distribution mean is a property of the probabilities that we use and is fixed. There's a similar kind of difference, okay, when we look at an entire population. If I imagine my population is all of the adult males, human beings in the world, then their mean, mu, is fixed. There's nothing I can do to change that. But the sample mean, well, if I take different samples of 100 adult males, I'll get different values for X bar. So sample values are things like the sample mean X bar, the sample standard deviation Sx, and therefore Sx squared. Remember, when we square standard deviation, we get the variance, and we're going to be using variance a bit more. So with the probability distribution, in fact, the two main symbols are expectation of X, which is the same thing as the mean. So the expected value of X is what we were talking about before. Okay, on a particular day, I'll get one of these values, but if I average them out over a very large number of days, then I get my expected number of lobsters per day. It's another name for the distribution mean, is the expectation. The distribution variance is called sigma squared. Okay, and it's got its symbol of its own, the variance. So the distribution variance. There is the symbol sigma to mean the distribution standard deviation, but I have to say the square root of the variance. So we begin to start using variance for some reason, for some purposes, in preference to the standard deviation. You'll see more of that later. So sigma means the distribution standard deviation. Okay, all right. One of the reasons why we talk about variance maybe more than standard deviation is the formula for variance of a probability distribution is simpler than the standard deviation formula. Obviously, to find the standard deviation sigma, I'm going to square root the variance. Okay, so my formulas for the mean and the variance, you are expected to know these. They're not in your formula book, okay, but they have the advantage of being extremely simple. So we're going to apply these formulas to some of the examples. Okay, let's start on example 2.5. Okay, so for this table here, we're going to follow up by using our calculator to do this, but we're going to start out by seeing how the formulas work. So for the mean, for mu, or the expected value, I need to be working out sigma x p of x. And in fact, all this part A asks me to do is work out x p of x and sigma x squared p of x. Let's do x p of x first. All that means is we take each x value and multiply it by the p of x. So I do 0 times 1/12, and I do 1 times 1/3, and I do 2 times 1/6, and I do 3 times 5/12. And the sigma means I add those all together. So I can type this in on my calculator as one big long calculation. Okay, well, my calculator told me that that was 23/12. Okay, and to do sigma x squared p of x, well, the p of x values are still a 1/12, a 1/3, a 6 and 5/12. But this says I have to multiply each one by x squared first. So I have to do 0 squared times a 1/12, plus 1 squared times a 1/3, plus 2 squared times 1/6 plus 3 squared times 5/12. Okay, so this is sigma x p of x without any squaring. When I do sigma x squared p of x, it's just the x values, not the probabilities, that get squared. And if you work all of that out, then it looks a bit like that, and you get 19/4. So here are my two answers to part A. Now I've got to go on and find the expectation, variance and standard deviation of x, which was the whole reason why I worked these things out in the first place. So I need to remember my formulas. So the expectation of x, formula is higher up the page. In fact, we've already worked this out, because the expectation of x is just the x p of x, also known as mu. So the expectation of x, also known as the mean, is the 23/12 I've already worked out. Great, okay. Decimals is fine, by the way. We're going to get decimals later. So in fact, okay, let's work out 23/12 as a decimal. So 23 divided by 12 is, there we go, 1.91667. Okay, so more significant figures than I need. Never mind. Let's work out the variance of x next. So I've got a formula for the variance of x. Once again, you have to learn it. So the formula for the variance, yes, it's got sigma x squared p of x in it, but it's then got minus mu squared. So my variance is sigma x squared p of x minus mu squared, which is going to be, well, sigma x squared p of x is this 19/4. Okay, and then I need to do minus my mu, which is 23/12 squared. So I do that subtraction on my calculator. I'm going to do 19/4 minus the previous answer squared, and look, it tells me it's 155/144, which is another way of writing 1.07639. Again, more significant figures than I'd normally need. And finally, I'm asked for the standard deviation. So this thing here is my sigma squared, it's my variance. The standard deviation is just my sigma. Okay, it's not an SX because this is an underlying distribution standard deviation, not a sample standard deviation. So I need to do the square root of that previous answer, 1.07639. Calculator, I just have to do the square root of my previous answer, which is a decimal, is going to give me 1.03749. Okay, so I have my three answers: standard deviation, variance, and mean. Okay, but now it says, part B, use the formulae first, then check your answers using your calculator. So all I need to do is go into my stats mode on my calculator and enter the data into the calculator. Now I've done that here, all right, but the way I've done that is the x values are 0, 1, 2, and 3. And then I've used the probabilities as the frequencies. So where you can see that value there, all right, I've actually typed in, you can see 1/12 then is the frequency. It's converted it to a decimal, but it accepts the fraction. And if you go down that column, you can see I've got my 1/3, my 1/6, and my 5/12. All I need to do now is my normal process for getting means and standard deviation. So if I press option and I do one var calculations in 3, then it's telling me some answers. So it's telling me that x bar, for example, is 1.916, which is what I got before. So that's confirmed from the calculator. All right. There's not a lot of working I can show, because normally if you're using your calculator, you would just write the answers down. Now, difference from what would normally happen. Normally on the calculator, we're interested in Sx and s squared x. But you can see there's a blank for s squared x at the bottom of this screen, and Sx is normally at the top of the next one. There's a blank for that, okay? That's convenient to us, okay, because it reminds us that we don't use Sx to talk about the standard deviation of the distribution. That would only be for a sample, and we would call it sigma instead. And lo and behold, the values I've got for sigma and sigma squared, if I can get a good shot of the calculator display, the values for sigma squared and sigma are exactly the correct ones. So when you're using your calculator, you put in the probabilities instead of frequencies. Your calculator doesn't even tell you Sx and s squared x. It tells you sigma and sigma squared in exactly the form you want. So I can see that the 0.076 is confirming this one, and the 1.03749 is confirming that one. So your calculator is a really good shortcut, and that's what we're going to use unless the question, like this one did, makes us use the formula.